Suppose we start in Canberra and we take a big trip across the Pacific Ocean to the United States. And on the west coast of the United States, in Washington State, is a place called Hanford. Now, the Hanford site is famous for being the place where the Americans made plutonium to put in the first nuclear weapons. Now it's a big nuclear waste dump, and you can still take a tour of it, I gather. Nearby is a far safer scientific facility. This is a giant Michelson interferometer. That white building there contains a beam splitter and a laser. The laser is split into two parts. One is sent along this 4-kilometer long pipe that's pumped down to a high vacuum. The other part of the laser is sent along this other 4-kilometer long pipe, which is at right angles. The lasers bounce off mirrors at the ends of the pipe and recombine at the beam splitter to form the interferometer. This is what it kind of looks like on the inside. There's the laser bouncing off the mirrors. And what we're detecting here with this interferometer is relative motion of the two mirrors. The light, which is split in half by the beam splitter, travels along to the mirrors and bounces off the mirrors. And because the distance the light travels depends on how far these mirrors are away, the interference condition will change depending on the relative length of the arms of the Michelson. So if these two mirrors start moving, then we see constructive and destructive interference of the laser at the output over there on the right-hand side. If everything's perfectly aligned, we would see the light flashing on and off as these mirrors move backwards and forwards. So what is the point of this giant Michelson interferometer in the desert in Washington State? The point is to detect gravitational waves. This animation shows rippling of space and time as a neutron star spirals around a black hole and approaches closer and closer, and eventually the two collide and annihilate. Well, rather the black hole eats a neutron star, I suppose. Now, this rippling of space and time can move the mirrors of the Michelson interferometer, and in this way we can observe a gravitational wave. The catch is that over the 4 kilometers of this Michelson interferometer, the relative distance of the two mirrors will change by about 10 to the minus 20 meters. That is a really small number. So Michelson interferometers can be phenomenally sensitive. What we're going to do now is calculate how Michelson interferometer works and see just how good the LIGO interferometer is. We've seen how big an interferometer can get. Now let's have a look inside and see what makes it tick. On one side we have a light source. We're going to consider the light source to be a single frequency of light, a laser. You can use other sources of light in interferometers. A white light interferometer is super interesting and actually really useful. But we're going to think about a single color of light for now. It's the easiest way to run through the calculations, basically. So we have an input beam here. It's split into two. It might be exactly half, it might not. Actually, one of the advantages of Michelson is it doesn't matter so much if it's not exactly a 50-50 split of the beam splitter. Either way, we have two paths, two different Michelson arms going to two different mirrors, and the light is reflected back from these mirrors towards the beam splitter, which gives two outputs to the Michelson. One is this reflected output beam that comes down here, and there's also light that can be reflected back toward the laser. What we're going to do now is calculate the output beam. We're going to calculate how much light comes out down here. So now it's time to do a calculation of how the Michelson works. We're starting with some light here. We're going to call the field of this light, the optical field, E in. It's coming into the interferometer through a beam splitter where it's split in half. Some of it goes up to this mirror here, some gets transmitted. That light's reflected from the mirrors back to the beam splitter, where some is reflected and some is transmitted. And the resulting fields that come out, we've got a reflected field here and an output field here. We just call this one reflected because it's coming back in the direction where the input came from. The arms of the interferometer have lengths L1 and L2, so I'll refer to this as arm 1 and arm 2. And I'm going to redraw the system just by displacing the beams on return to the beam splitter. That's totally fine. You can build an interferometer exactly like this. It's just easier to analyze because now the place where the beams come back and interfere is just a bit offset, and we can see a bit better what's happening. Okay. The other important thing to realize is that because the light travels around this path, this arm 1 and arm 2, as it travels along this path, it accumulates a phase. As you travel along a wave, the phase changes. And we have a phase phi1 and phase phi2 for the two arms. Now you can consider this in two different ways. One would be to follow along the length of this arm as you travel, a distance L1 here and a distance L2 here, and then back again, so 2L1 and 2 times L2. And then you say the phase change as you travel along that length is k times the length, so 2k L1 and 2k L2. That would be the phases phi1 and phi2 in terms of k and length. Alternatively, you could sit here and say, how long does the light take to travel to this mirror and back again? And then we have a time t2 and a time t1 for each of the arms. And the accumulated phase then would be the frequency omega times the time. So you can calculate the phase using the time it takes for the light to leave the beam splitter and return back, or the length times k. Either's fine, but don't do both, just choose one or the other. Alright, now beam splitter has the following important properties. We have light coming into the beam splitter, and some being reflected, some being transmitted. The light that's transmitted off this front surface of the mirror will give the phase a phase of pi, so negative r. So it's got an amplitude reflection coefficient of negative r, and amplitude transmission coefficient of t. That means that there's a phase shift between the transmitted and reflected light of 180 degrees, or pi. The relationship between r and t is given by this, so the square of r plus the square of t must be equal to 1. And this is all about energy conservation. Now light coming back from the other side, well, in this case, if it's reflected off this side, the reflection coefficient is positive, and so there's no phase shift between the transmitted and reflected fields when it comes and bounces off the other side of the mirror. And this is a property that's required for conservation of energy. Now, the light that comes back from this direction is the field E2, which has a phase shift phi2 because it's travelled this arm of the interferometer. And so the field that's reflected and transmitted here will be E2 times r and E2 times t, where E2 is given by all of this in terms of E1. We can do exactly the same thing for the light that comes back from arm 1. It will hit the beam splitter, some is reflected, some is transmitted, and on this side we get a negative r, on this side we get a positive t. And now all we have to do to find the interference, that is the total amplitude of these waves, is add these amplitudes up to find the total amplitude, and then to find the amount of light, the power of light, we take the absolute square of those amplitudes. So now we're going to add up these amplitudes. So E out down here, this E out down here, is given by the sum of r times E2 and t times E1, where E2 and E1 are these fields that are coming back from the arm. And as I've said, the fields E1 and E2 can be written in terms of a phase shift and the original input field and the reflection transmission coefficients. So you can follow that through. We can rewrite this sum. Sorry, I left a 1 here. Forget about that 1. That shouldn't be there. So we can rewrite that in terms of E in, R and T, and just these complex exponentials here with the phase shifts phi2 and phi1. I can take out a factor of phi2 here and then express this just in terms of the phase difference, a delta phi, phi2 minus phi1. And this is an interesting way or useful way of writing it because it really shows you that the interference pattern here depends on the relative phase phi2 and phi1. We don't care what the total values of phi1 and phi2 are, we're just comparing them. So this phase factor that comes out the front here, when we take the absolute square, it'll go away. And so all we're left with is a relative phase. To calculate the intensity or the power at the output, we take the absolute square, and to do that we need to find the absolute square of this complex number. So I've expanded the complex exponential here in terms of cosine and sine, then I square the real part and the imaginary part, which is where this expression comes from. And so finally I get an expression for the output power or intensity, which goes like 1 minus the cosine of a delta phi, where delta phi is phi2 minus phi1. And that's the power at the output of the interferometer. And we can see that as we change the phase, we'll change the intensity. The last thing we have to do is relate the phase shift that we derived previously back to the arm lengths L1 and L2. So here's the expression for the output power, output intensity. It's given by something that's proportional to 1 minus cosine of the phase difference, phi2 minus phi1. You sometimes also see this written as a sine squared function, which you can get using this trig ID here. Okay, so what about the phases? Well, for the path length L1, we can just say that the accumulated phase shift, if you follow the wave around, is just given by the distance times the k. So k is 2 pi on lambda, the distance is 2 times L, so phi1 is 4 pi L1 on lambda. And it's similar for phi2. Of course, if we dunk the whole thing in water, then lambda would become shorter by a factor of the refractive index, but we're assuming here we're dealing with a refractive index of 1. So we can substitute in these values for phi1 and phi2 and find an expression for the output power as a function of L2 minus L1. So what we see here, if this path length is exactly the same, then sine squared of 0 is 0, and we have no output power. But if the path length varies by just a quarter of a wavelength, then we would have pi on 2 here, which gives us a sine squared of 1, which would be the maximum intensity. And as you vary L1, L2, they don't have to be exactly the same or even close to the same, you will pass through fringes of bright and dark every quarter of a wavelength. And so in this way, the wavelength of light becomes a tick on an optical ruler. What is meant by that is that as you vary the relative lengths L1, L2, for example, if a gravitational wave is going past and this mirror moves a bit further away from this beam splitter, then you're comparing that length, that change in length, to the wavelength of light. Now, if the wavelength of light here is, let's say for a 1 micron wavelength that they use in a gravitational wave detector, that's 10 to the minus 6 meters, then you'll go from a full bright fringe through a dark fringe and back to a full bright fringe in half a wavelength, which is half a micron. So that's a pretty good ruler. We can easily determine distances much less than half a micron by measuring changes of intensity sort of fractionally as this moves. But that's a far cry from where we want to be with LIGO. So remember, we're trying to measure a change in path length between L2 and L1 of something like 10 to the minus 20 meters, which is a good number of orders of magnitude different to where we are with 10 to the minus 6 meters or so. How do we get all of those orders of magnitude back? Well, there are a lot of other tricks in the LIGO interferometer that we haven't included here. The light doesn't just bounce to this mirror and back to this beam splitter. There's actually another mirror here and another mirror here that recycles the light backwards and forwards along these arms and amplifies the change in length, as the signal from the change in length, as the light circulates around and around. There's another mirror here that reflects power back into the interferometer to increase the amount of light. There's another mirror here that also reflects light back into the interferometer. The whole thing is extremely complicated with mirrors all over the place. But the point is that by building these kinds of devices, you can achieve extraordinary sensitivity to changes in length. And incredibly, we can measure these ripples in space and time. There's actually a lot more we can say about the Michelson and different calculations we can do. In this case, we've treated the waves as being ideal plane waves, so the interference is constant across the face of the wave. But we could also imagine dealing with something like spherical waves, where they have some sort of shape, and then you end up with an interference pattern, some sort of circular pattern because of the curvature of the waves. Or we could deal with misalignment of the Michelson interferometer, where one of the mirrors is tilted and we end up with fringes like this. So there's a lot more we can say, and some of these things you'll deal with when you have the opportunity to build and use a Michelson interferometer in the second year labs. But we'll leave that till next year.